Sorry, I'm not sure why my screen went blank, and I finally figured it out. I accidentally hit the fade to black button, totally accidentally. I was wondering why everything just suddenly went dark. Hello everyone. How are you today? Oh, let me turn this down. So, I am kind of behind the... Get a little behind. Well, good morning. How you all doing today? It's a great Thursday, isn't it? Oh, I suppose you're wondering what we're going to do today. You saw the slides just a moment ago before everything went dark. We are going to be working on the next assignment, which is going to be cracking hashed passwords using this time a dictionary attack rather than a brute force like we did last time. So we're going to be using a dictionary of possible candidate words that we could use for our possible passwords, and then we will crack the passwords based on that. I need to move my camera just a little bit. I can see it's just a little bit off center. There we go, right over there. And it's actually a little bit crooked, but I don't want to fix that. Actually, I guess I can fix that right now. Reach over here, and just tilt it a little bit, and then hopefully it doesn't shake too much. There we go. All right. Well, let's go ahead and get started on this. I guess before I want to get into writing that program, I want to show you a little bit about how to work with large projects, because we're starting to get into programs now that involve multiple source files. We've already seen how to compile some of those. You just list out each one of the C files on the command line. But a couple of issues come up. One is the command line is now becoming longer and longer, so you'd like to be able to automate that. And two is, as the projects get bigger, there's more and more work to do for the compiler. I mean, these days, the computers are fast enough that you don't really notice when a larger project with 2 or 3 or 4 source files is being compiled. It still seems to take about the same amount of time. But if the project involves hundreds of files, then it can take longer and longer to do. Like, let me show you an example of a project that's a bit bigger and would actually take not a trivial amount of time to compile. So there's this program out there that I think is a lot of fun called Figlet. Uh-oh. Let me go ahead and just do a search for it. Make sure I have wound up at the right site. Here it is. So this program has been around for like decades. I remember using this in college and university in the 1980s. So it's been around for a very long time. And what it does, it's just a fun little program that takes a little bit of text and it turns it into big characters using just characters that you find on your keyboard. So, and you can use different fonts, right? You got this font here, you got this font and this one. So this program is easy to download, easy to compile, and get it to run. So let's go ahead and just, let's see, if we go here, nope. What I want to do is I want to download this program. Let's see, here it is. So I'm going to copy this address and then come over to my environment over here. Nope, I don't want to open a new file. I want to open a new terminal. And let's drag this up to the top so we got plenty of space. So I'm using here a program called wget. And it's basically a program that will fetch a file off of the internet. You just say wget, you paste in the URL to the file you want to download, and then it just goes and downloads it. So right now I've got a file here called figlet-2.2.5.tar.gz. The gz on the end means that this has been compressed. It uses an algorithm called gzip, which is, I guess it sounds like zip from Windows, but it's not quite the same. The zip program on Windows is designed to take a whole bunch of files and package them together into one container. The gzip algorithm only takes one file and then compresses it. So there's another program called tar, which stands for tape archive. And its purpose is to take multiple files and put them into one package. So there's the tar program, which just packages up multiple files. And then there's gzip, which just compresses them. So you use both of them together, and then you get what appears to the casual user to be more or less what a zip file is. So I'm going to uncompress this. The X here means I want to extract the contents of the archive. V means verbose, and it means I want to see the progress as it's doing it. And then F here means the following command line argument is the name of the file to unpack. So here's the program. And let's take a look here. So there is in here a file called Makefile. And this file contains the instructions for building the entire Figlet program. If I just type in make is a program that will get its instructions from the Makefile, and then the Makefile contains the commands that it needs to actually compile this program. So it didn't take very long, and there's actually a bunch of warnings here about something called z-ungetc. And it's, well, they're just warnings. And I can see what the warning is now. I'm not going to be worried too much about it. It says, right-hand operand of comma expression has no effect. Here's the expression. So it looks like one of these is used to decrement a variable, another one's used to increment it, and then this third one here just is like sitting by itself. It's just the variable c all by itself, and it doesn't do anything. So that's what this warning is. So it's just a warning. But it looks like the program compiled. And now I should now have an executable here called figlet. So if I type in figlet and then, whoa, oh, I see. I need to go make install. So again, another set of instructions for copying the executable and all of its associated support files into an installation directory. And now I should be able to type in figlet and some text, and then it makes it nice and big. And I can even change some of the fonts. Let's see, how do I find out what are the fonts? I guess what I can do is I can just look in here and see should be a directory called like, oh, show fig fonts. How about that? Show fig fonts. Oh, here we go. So these are the fonts that come installed in it. So one called banner, one called big, I think that's the default. One called block. There's bubble, digital, curvy, lean, it's kind of leaning over, mini, mnemonic doesn't seem to do much, script, shadow, slant, small script, small shadow, small slant, standard. Oh, this is probably the default one here, and term. So I think if I go figlet-f, mini, yeah. So back in the day, if you were using one of these Linux systems, now back then they were like shared systems. So there would be a central server, and then maybe everyone who was in a class would log into that one computer and use it simultaneously. So usually when you logged into the computer, there was some kind of welcome message like, welcome to the computer science department Unix server. And it typically was written in nice big block letters using a program like Figlet to make those big block letters. So that's where I got introduced to this program. So what I wanted to show you there was that compiling and installing this program is not a trivial matter. You have to know which files to compile. You have to know which, let's see, let's scroll way up here. You have to know which files to compile. You have to know maybe what order to compile them in. And then you also have to know how to assemble all those things into a working program. And in fact, there's multiple programs here. There's one called checkfont, there's one called figlet, one called figlist, show fig fonts. So there's multiple files that need to get built. And then there's the separate step of installing everything, taking all the executables and moving them into the system directories, and taking the font files and moving those into the system directories. So there's a lot of things that need to be automated in order to compile and install this program. So this file here called Makefile contains those instructions. See, when I typed in make install, it executed these instructions. So what we're going to do today, one of the things we're going to do today is learn how to, oh, you don't see what I'm doing, what I'm showing you here. Here we go. So this is the Makefile that came with Figlet, and it contains the instructions for building the Figlet program or programs out of the source files. For example, down here, when I typed in make install, it executed these 7 instructions using some variables here to configure where they get installed. So one of the things we're going to do today is learn how to build those files. Now, a lot of you are watching my live stream because you came here after watching my video about using Makefiles. It turns out that's one of the most popular videos on my channel, which you know, really thrills me actually that I've done a service to the community by making a video that really, a lot of the comments I get is it really breaks down step by step what's going on inside of a Makefile. But if you haven't watched that, I'm going to give you a quick rundown of what's in there. Okay, so when you compile a program and you type in the name of the compiler and then the C source file, it actually goes through a whole series of steps to get you from the source file to the executable. So you start with a .c source file, and then the first thing it does is it runs through a phase called the preprocessor. So the job of the preprocessor is to handle things like the comments. It strips out all the comments, and it also handles things like the hash defines and the includes as well. Let's see, where can I put notes about that? I'm just going to erase this. Make this box bigger. Here we go. So this handles include, define, and comments. Okay, so once it goes to the preprocessor, comments have been removed. The files that have been included have been copied and pasted right into the source code, and the defines as well it's gone through and found all the places where it needs to do a search and replace, and it's done that. So by the time it gets done with the preprocessor, all of the hash directives have been removed and executed, and the comments themselves have been stripped out. So the next phase after that is to take this preprocessed source code and now go through what really is actually the compiler. And so this is going to translate C into assembly language for your target architecture. Okay, and then out of that goes into the next phase, which is the assembler. And this is going to translate assembly file into what's called object code. This object here has nothing to do with Java or C or C++ objects. It has to do with, I guess it's the compiled binary code. And I guess the object here, the thing that it's directed toward, is the actual architecture that you're compiling for, like an Intel architecture or an ARM architecture. Okay, and then goes into the linker. And here it gets joined, join with libraries. Sorry, my handwriting is terrible this morning. And then finally, out of that is your executable. So these are the steps that the compiler does every time you just run the command. It goes to the preprocessor, then the real compiler, then the assembler, then the linker, and then finally you get the executable. Along the way, some intermediate files get generated. After you go through the compilation stage, you end up with a .s file, the assembly language file. You don't normally see that file. It gets erased after you do the compilation step, but it's there. And then after you do the assembly step, you end up with a .o file, which stands for object. And then finally, after the linker is done, you end up with your executable. So you can stop this process of compiling at each one of the stages. like after the preprocessor stage, you can say -E, capital E, and it will show you the output of the preprocessor. So it will just basically stop the process there and then either save a file or show you on the screen what resulted from doing that step. Then after doing the compilation step, you can say capital S, and it'll show you the source code, the assembly code file. After doing the assembly step, you can say -c, and it will show you the object file. And then finally, you've got the executable at the end. So for example, here's our brute force program that we wrote last time. So if you remember how we compiled that, we went clang brute force.c, md5.c, because we needed 2 C files to get this done, output to brute force, and then link in the crypto library. Okay, so let's draw a picture of what happened there. So we started with, now this time I'm going to draw the diagram going upwards. So the steps here are drawn going this way, but I'm going to draw this diagram going up. So I'm going to start with this is actually totally confusing. Let me draw a line. So brute force.c and md5.c. When I'm compiling these, what actually is going on behind the scenes is it takes the first C file that I've listed, it runs it through the preprocessor, then it generates the assembly language file, and then it generates the object file from that. And then it stops for a moment because it needs to catch up with the other program. So what I'm going to do is I'm actually going to compile this sort of like by hand, and then we will assemble it into, or link it together to make a complete executable. Actually, let me show you here on the screen what I'm going to do here. So I'm going to go clang brute force.c, but then I'm going to say -c on the end. And over here you can see I've ended up with the object file. I went through the preprocessor phase, through the compilation phase, through the assembly phase, and then I stopped at the object file. Okay, and then I'm going to say clang md5.c -c. And now I've got down here an md5.o file, the object file for that C file. And then finally, I'm going to link them together. I gotta type. Oh, my typing's terrible. Okay, so I'm going to take the object file produced by the compilation of the brute force.c. I'm going to take the object file produced by the compilation of md5.c, output to an executable, and then link in the crypto library. And then I need to spell correctly, so let's go back and fix that error. There we go. So that makes a complete executable that is now runnable. So let's go over here and let's draw a picture of what happened. So I took my brute force.c file, and then I did, let's see, what command did I do? I did clang, I'll put the option up front, clang-c brute force.c, and then that produced brute force.o. And then also I took md5.c and then that produced md5.o. Okay, and then those two got brought together with clang brute force.o, md5.o, output to brute force, and then also link in the crypto library. Okay, so in addition to my two object files, I've got lib crypto, which is sitting off in the system directories, and those get brought in. And then finally, I get out of that my executable. So when you run the compile command and you link in a library, what it literally does is it just takes the word that you typed in after -l, it sticks the three letters lib in front, and then .o on the end, and then it goes off and it finds that file. It finds libcrypto.o, and that also gets linked into your program. What does the O extension stand for? It stands for object file. It doesn't mean objects like in a Java or C++ sense. It means object as in like the object of my compilation, the architecture of my compilation is what I'm compiling for. So my objective is to compile for an Intel architecture. In this case, I could compile for an ARM architecture. That would be my object there as well. Someone's asking here, where can I find the MD5 file? So let me show you. Let me paste into the chat where you can find those. Give me a moment. I think this will do it. Let me know if you can't get into that. But you should be able to click on that link, and then that'll take you over to a Bitbucket repository where you can get some of these files that I'm talking about. Okay, so let's see if we can automate this. So I'm going to make a file here called Makefile. By convention, starts with a capital M. It doesn't have to, but by convention it does. I guess the reason for that is usually when you get a file listing, file names that start with a capital letter end up towards the top of the listing. Ones that start with a lowercase letter end up towards the bottom of the listing. So I think a lot of programmers want to see those kinds of files up front. So I think that's why they capitalize it by convention. So a makefile consists of a series of what are called recipes. So a makefile recipe consists of three parts. It contains a target, then a colon, then a list of prerequisites or dependencies. And then down below that line is one or more actions that are used to turn those prerequisites into the target. For example, if I want to turn the bruteforce.c file into the bruteforce.o file, my target is the .o file. That's the thing I'm trying to build. Then a colon, then a list of the file or files that are used to build that .o file. In this case, it's bruteforce.c. And then down below, you have to indent with a tab, and it has to be a tab. You can't use spaces. It must be a tab. You put in the command or commands that you would run in order to turn this file into this file. In that case, it's clang-c bruteforce.c. Likewise for the MD5 file. If I want to turn the MD5.c file into the MD5.o file, I write a recipe for that. And then finally, when I want to take those two .o files and assemble it into the final executable, my target is the name of the executable. It depends upon or has a prerequisite of having built the .o files first. And then finally, the command I use to turn those two .o files into the final executable. And you can see that these three commands are just the same as the ones that I used over here. This one, and then this one. So let's go ahead and build that Makefile just like I've written here. Now, in my picture, I've got the executable up here at the top, and I've got the things that it depends upon, the intermediate files, working downward to the tree. So you should build your Makefile the same way. The thing that you're trying to build goes up at the top, and then you work your way down. Let's see, there's a question on the chatter. What are .md files? I guess someone's looking inside of the Bitbucket repository that I've posted for making some of these files available. So MD stands for Markdown, and those are a special way of formatting text files so that if you turn them into HTML files, then you can have bold, you can have big writing, you can have writing in terminal font. And so it's just a quick way to format text files so that they can be read by a web browser, or they can be read by just a human looking at it, and it looks kind of like there's headings, and it looks kind of like there's commands embedded in the file itself. So MD stands for Markdown. Okay, let's build this Makefile. So up at the top, I'm going to put the name of the executable and its two prerequisites. So the prerequisite for the executable is that the .o files exist and have been built already. And then I hit Tab to go over into the next line, and I'm going to type in the command that's used to build. Oops, I didn't mean to do that. To build this executable out of these two files here. And then I work my way down the tree. So the next recipe I'm going to put in here is how to build the .o files out of the .c files. all these pop-ups that keep coming up, I kind of hate those, because usually 95% of the time they don't contain what I'm looking for. And so I kind of ignore these. I mean, I don't want to put in change, check font, clean. I don't want to put any of that stuff in there. So I'd rather almost myself just have this pop-up like not appear. It's just really kind of annoying. See, like there, it just changed my lowercase c to an uppercase C. I don't want that. I want a lowercase c. See, you end up fighting against it. I'm hitting escape in order to get it to go away. You know, I'm going to go here to my preferences. Let's see. What is that called? Completion? Okay, I'm not doing tab completion. Word-based suggestion mode. No? How about suggestion? Now, controls whether completion should be computed based on words in the document. Maybe that's what I want. Suggest on trigger characters. So let's take that off. See if that helps. Let's try typing this command again. Clang dash. Oh, this is much better. Yeah. I know it's the IntelliSense like suggestion, but I end up fighting against it all the time. And I'd rather just type things in myself than depend too much upon what's popping up there. I mean, if the pop-up is good and it gives me a good suggestion about what to type, yeah, I kind of like that. I'll just hit tab and get it to complete. But in this case, it was giving me poor suggestions. I don't want those suggestions. So I'd rather just turn it off. It's just annoying to have it pop up all the time. Okay, so I've written my Makefile. Let me go ahead and save this. Now, I'm going to remove all of those intermediate files. And then let's type make. So make is the program to run. Make is going to use the instructions in the Makefile in order to build my executable. And you can see it just very quickly ran through and typed in, for me, those 3 compile commands in order to build the brute force executable out of the object files, and then the commands to build the object files out of the C files. So it compiled bruteforce.c, and the result of that was bruteforce.o. It then compiled md5.c and produced md5.o, and then finally it linked all those together along with the crypto library to build my executable. So whenever I type make, it's going to automatically run through and build my program out of the 2 source files. Now I don't have to type in that whole command line again. And you know, you usually only have to type it once, right? And then you use the up arrow key to get your previous history back. But sometimes that previous history goes back several lines and you have to go like hunt it down. It's just really handy to have this Makefile sitting there ready for you to just type make, and it just builds your executable. The other nice thing about make is that it does conditional compilation. If I type make again, it says there's nothing to do. Brute force is already up to date, because it knows that I haven't changed my C files, and therefore there's nothing to do to rebuild the executable. If I then go and change something about my C file, let's say what can I do here? I can just do something simple, like instead of just saying found it, I can say found the word. And then if I save that and type make, it rebuilds my executable, but it also knows that it doesn't have to do anything with the md5.c file because that one didn't change. it only recompiles what it needs to do in order to build that executable. You can see how this would be of a great benefit if you had a large project with hundreds of files. If you just change one of those files, there's no need to go and recompile all 100 of them. You only have to recompile the one that changed and then link it together. And the linking phase usually doesn't take very long. I have a friend who works at Google, and he works on the Google Chrome browser. That browser is made up of not just hundreds of files, but probably tens of thousands of files. If you were to try to download the Chrome source code or Chromium source code and compile it on your computer, it might take a couple of hours to do. There are just so many files to do. It's like start the build and then go have lunch and then come back and it might be done. But you only have to go through that painful process once. If you then subsequently just change one file in that entire source code repository, it just recompiles that one file and then links it all together, and that just takes a couple of seconds to do. So when you're building a large project, you have to go through and build the whole thing once. And then tiny changes you make from that point forward go very quickly. That's the benefit of having this Makefile, is it goes and it finds all those dependencies for you, recompiles them, and then relinks it together. Okay, let me see if I can catch up on some of these comments here. So what does make do if you just type in make? So first of all, I can type in make followed by one of these targets. So if I want to kind of like want to force it not to, if I want to force it to build one of these targets, I could type in make md5.0. It would still say it's already up to date, but I could, let's say I could remove md5.0, and I could just say make md5.0, and it would just do that one command. So the default behavior, if you just type in make by itself, is to look for the first recipe and build that thing. Otherwise, you could type in make and the name of a target, and then it will go straight down to that target and apply that recipe. So a common thing to do is to put in a recipe for some commands that you want to execute, but you don't necessarily want to compile anything. For example, if I want to run this brute force program, I'm going to run it with brute force and then the hash that I want to try to crack. So normally I would type in, let's just build this thing again. I would type in brute force and then a hash that I want to crack. And I've already forgotten what the hash is. So let's go ahead and come up with a hash for it to crack. Oh, let's see. Let's remove this. Let's put in, where is it? RC4. What am I looking for? Morse code, Enigma machine, encoding, integers, cryptographies, blocks. Here we go, hash functions. And we'll do MD5. And we'll put in a nice 5-letter let's see, can I just view this as bytes? And we're going to group by none. There we go. Okay, so let's put in a 5-letter word here. Let's put in, how about March? Like that. So here is the hash for March. Let's go ahead and copy that. There, found the word, it's March. Okay, so you run the program and you put in the hash that you want to crack, and then it runs through all the combinations. So let's put in a target here so that I can just say like make, I don't know, make and then some like, I don't know, let's do like this. Let's go Oh, I've got to come with a name. I'll just call it March, right? So what I'm going to do is I'm going to run the brute force and then with this hash right here. Okay, so now I can just type in make March. Now I know what the answer is, right? And then it just runs the program. It puts in my hash and then runs through all the combinations, and then eventually it'll find the word right there. And let's do another one. Let's do, I'm looking around my room here going like, what 5-letter word do I see just laying around? Oh, I see my dog here, so let's put in puppy. So here's the hash for puppy. So notice these recipes don't have any prerequisites. So they are just recipes that are just going to run when you type in make and then the name of the target. So you type in make March and then it just runs that command. Type in make puppy and it just runs that command. Save it, make puppy, and then it runs through all the combinations there. Oh, Akash is saying, isn't brute force technically a dependency for March? And you're right, actually. If I was to remove the brute force program and then say make March, it would go ahead and try to run the brute force program and it's not there. So it actually would be a good idea to put in brute force as a dependency so that if I run make March and it sees that the brute force program doesn't exist, it'll go and build it. See right here, I said make March. It went and checked and saw that the brute force program didn't exist. So then it found the recipe for that, and then it built the brute force program out of the existing object files that I already had. So that's a good idea. Why couldn't we just have a direct target from the C files? Why do we need to make the intermediate.o files? The reason for that is so that we can do this conditional compilation. I mean, you're right. We're only doing compile out of two files, so it just takes a fraction of a second to do both of them. But I want you to think about, as you're building these make files, of building that complete dependency tree so that if you just change one of the C files, it doesn't have to compile everything all over again. Like, I could have just said here, let me go ahead and just duplicate this. I could have said brute force is built out of .c, md5.c and brute force.c, and then I compile this and then compile that, right? So anytime I change one of the C files, it'll go ahead and just rerun that command. But it's a little extra work for the compiler because it also has to compile the md5.c file, which didn't change at all. Again, for a really small project, it doesn't matter a whole lot. But if your project gets bigger and bigger and bigger, you're probably going to want to have it only compile the files individually, so that if you change one of the files, it just recompiles that one into its associated object file and then links the whole thing together. What if you wanted to send this makefile to someone who used GCC instead of Clang? Would you need to make another makefile for them? You could, but you could also use variables. This is kind of advanced makefile stuff. Up at the top, you could say something like, typically the convention is to say cc equals, and then, so here, and then some value. So here I'm making a variable called cc, and the value is Clang. And then in place here, I can do $ parentheses cc, and that is to look up the name of the variable, the value of the variable. Okay, so let's remove md5.o and brute force.o and the brute force executable. And then we'll just do make. And you can see here that it swaps in the name of the compiler for that CC variable. So all I have to do if I want to switch compilers is just change this to GCC. Let me save it. I'll remove those intermediate files, type make, and then now it's using GCC instead. So typically when you distribute a Makefile to someone else, you tell them in the documentation, go and change that line so that it uses the compiler that you happen to have. Could it take the compiler name as an environment variable? Yeah, it could do that as well. So I could take out this line. Let me go ahead and remove those. And then I could say cc equals clang make. Oh, that did not work like the way I expected. Did I save this? Oh, I didn't save it. There we go. There we go. So I define the environment variable, and then I call make, and then it just gets passed right into the Makefile. But then if I type make by itself, in that case, it uses the default value for the CC variable, which is just CC, C compiler. And I think on my system, there is a C compiler, and it's just a link to etc. alternatives CC, which is itself a link to GCC. So when you call CC, it's really just calling GCC. So I'm going to go ahead and put up here the old clang so I don't forget. Let's see. Oh, so make command doesn't work on your environment. So if you're running on a Windows system, make is not one of the default commands. You probably should, I would suggest, install the Windows subsystem for Linux. That will install a little tiny Ubuntu distribution on your Windows machine. And then from there, you probably do have things like GCC and make at that point. If you don't, you can always install them pretty easily. On an Ubuntu system, you can say sudo make sudo apt install. I think it's called. Oh, now I'm forgetting what it is. It's there's one package you can install that just installs all the stuff for compiling programs. It's called, I think it's called build something. Now I'm totally blanking out on what it's called. Oh, maybe someone can remind me what it's called. But it's, yeah, sudo apt install build something. If you're doing actual Windows programs, you want to build Windows programs, then you should probably install something like Visual Studio. Not Visual Studio Code, which is just an editor, but actually the Visual Studio compiler package that you can get from Microsoft. So if you actually want to build Windows programs, you're probably going to need something like Visual Studio, the full-blown integrated development environment. That includes the compilers and the libraries you need to build Windows applications. If you're just building command line stuff like I'm doing here, then the Windows subsystem for Linux will be able to at least get you mostly the same as what I'm showing you here. Oh yeah, build essentials. That's what I was thinking about. Sudo apt install build essentials. And that'll install compilers, make libraries, header files, pretty much everything you need to be able to start building C programs on a command line. Maybe it's build essential instead of essentials. Yes, you're right, build essential. Okay, so I think I've answered your questions. So again, if you run make without any arguments, it just looks for the first recipe and runs that one. There's one more recipe that I'm going to put in, and that's called clean. And the purpose of this one is to clean up all the intermediate files and leave behind just the source files. So to do clean, I'm going to want to remove md5.o, brute force.o, and my executable. So whenever I type in make clean, it'll just clean up all of the leftover files from the compilation process and leave behind just my source files. So that's kind of handy if you do want to reset everything and then rebuild the whole project from scratch. And it's a really handy command to have because it's really easy to accidentally remove too much. Like, let me tell you a story, and some of you have heard this story before. I was in a university. I was probably, I can't remember if it was my second year or third year, and we had a huge project to do. And it was going to take multiple hours to do. I think it was maybe in my data structures course, so that would have been third year, I'm guessing. Second year or third year. And back then, it was actually very unusual for students to have their own computers, like in their, in their homes or dorm rooms, because computers were just really expensive back then. This is the late 80s. If you wanted to have a typical, PC computer or an Apple computer, I mean, like, the one back here that I've got, this was the one that I didn't have this one when I was in college, but I wanted this model that you see right back here. This is the Mac SE30. That, I think, when it debuted, sold for probably about $4,000, and that's in late 1980s money. So the equivalent value today would be about between $8,000 to $10,000 for that computer. And that's just way beyond the budget of most university and college students. I didn't have that computer. I had what's called the Mac Plus. That one, I think, I worked all summer to afford that. It cost me about $2,000. So computers were really expensive. It was very unusual for students to have their own. Usually what happened was if you wanted to go work on a program, you went to one of the laboratories that the university provided for you with a room full of computers that you could go and use. So that's where we went. And it was, the nice thing about those laboratories, it was a great place to hold these all-night programming, like, these days you call them hackathons, but you'd show up there around dinner time, you'd sit down with your friends, you'd order pizza and sodas and chips and snacks, and you just work on your programs all night until they're done. So it's like a big party. And so I'm working on my program, and it's around 4 o'clock in the morning. And it's mostly working, but I've been working at it for probably about 8 hours. And, you probably had this experience. If you're working on a fairly large program, it mostly works, but there's a few cases where it doesn't behave the way it's supposed to. So you end up bandaging in these patches to the program to make it work. A whole bunch of conditionals, like if this case appears, then behave this way. And if this other case appears, then behave this way, otherwise behave the default way, right? So I was full of these conditions just to try to make it work. And like I said, it was mostly working, probably 95% of the way there. And I decided that I was just going to, at some point, wipe the files clean and just recompile from scratch. So I wanted to get rid of all the object files and just rebuild the program. And, at this point, I didn't have a Makefile. I hadn't learned about those things yet. So I was compiling everything by hand. I would type in the name of the compiler, CC or GCC, and then -C in the name of the C file. And then I'd work my way through all of the object files and then link everything together. But I wanted to start everything over from scratch. So here I am in my sleep-deprived 4 a.m., hyped up on pizza and chips. What I type in is I go RM, and my fingers, my brain was thinking I need to go star.o, right, to delete all those object files. But that's not what my fingers actually typed. What they typed was remove star space dot o. And so what happened there? Now, maybe some of you who are watching this can predict what happens in this case. What happens if I type in rm star space dot o? Now, I'm not going to actually do it, but what do you think happened? So what I get back if I press enter is, and now also the thing to keep in mind is the computers were slower back then. So I get back a message that says remove .o file or directory not found. And I go, that's strange, right? I didn't tell it to remove a file called .o. Wait a second. Uh-oh. And the other thing was it took about 5 seconds for this message to appear. And the reason it took that long to do is that it was going and it was removing everything, and then it said, there's no file here called .o. So everything was gone. All my work, the last 8 hours of work, was just completely wiped out. Needless to say, I cried for about 5 minutes. I mean, literally. I mean, I've been working so hard on this, and it was all just gone. And on a Linux system, it doesn't say, like, are you sure you want to delete this? It just simply deletes it. And there's no backups, right? At least there was no backups to go to at 4 a.m. in the morning. I didn't know anything about version control, didn't know about Make, right? I was a fairly young programmer. You're right, Git might have helped to prevent this disaster, right? But I didn't know about those things. So I just cried, and my friends came over and went, man, that really stinks. You just deleted everything. Sorry about that. What I learned that night, was first of all, I should make backups, right? I learned about that. But the other thing I learned was, first of all, this program was due at like 8 in the morning. I don't know why the teacher made these things due in the morning, but he did. So I had now about 4 hours to pull this thing together after deleting everything. And I did. And you know what? It took me 8 hours to make version 1 of the program that 95% of it worked. And it took me only about 2 or 3 hours to make version 2 of the program that worked perfectly. Why did it work perfectly? Because I had learned so much about the way the program was supposed to behave over that 8 hours that I was able to write version 2 and just integrate in all of those edge cases that I had been patching all this time and just barely getting to work. I had learned about the way it was supposed to have been written in the first place. And version 2 was just so much better than version 1. It was shorter, it was more compact, it was more concise, it just worked better. All of the edge cases were taken into account, and it was just, I was really actually quite pleased with the fact that it just worked almost the first time I ran it. And so to this day, I remember accidentally deleting all my files. And first of all, I try not to do that. And that's where the Makefiles can come in handy, because you only type in that remove command once. And then you never have to worry again about accidentally removing the wrong files, because you've written that command, you looked it over, you made sure it looks correct. So you just type make clean, and it just removes the files that you intended to remove and doesn't remove the other ones. And the other thing I learned was not to be afraid of starting over. I still do that to this day. Sometimes I've written a program and it's just like, it's almost working, but it's growing and growing, and the source code has more and more branches in it that try to take into account some edge cases that I hadn't considered when I started writing it, that sometimes I do just simply go like select all, delete, and just delete the whole file, and then start over again. And usually version 2 is much better than version 1. So those are like the two things I learned out of that experience. One was, don't be afraid of starting over, and the other was, usually version 2 is better than version 1. Oh, and I guess the third thing is, if you really don't want to deal with that stuff, use a version control so that you can get your backups back. What's the use of writing programs in so many .c files? So putting everything into one C file will make it very difficult to read and modify. So like the C file could just be huge, right? Instead of just being nice and compact and being able to see almost all of it on one screen, now it's this huge thing that you have to scroll through and find the individual functions. And also you might want to actually be writing multiple programs that use some of the same functions. We can see in this figlet program that we had worked on. Where is it? Here. I guess over here. Oh, let me look on this. Here we go. This is what I'm looking for. So this figlet program comes with 1, 2, 3, 4 executables. And a lot of those executables share some of the functions in common, like to be able to load in some of these font files. So you need to have some functions that are shared amongst those executables, and the way to do that is to put them into their own C files so that you can link those object files together. Abdul says, me too, I built the same project 4 times, and every time you did it, it became better than the previous one. That's so great to hear, right? It's a good, like, you know, just programming life lesson about working on these projects, that sometimes the next version is better than the one you just wrote. I have other stories about other times when I accidentally deleted too much stuff. I'll tell some of those, you know, on other days. But having worked in the IT field for many years, those things happen. And you can cry about it. You can hope that you had backups, but some cases you don't have backups. And then you can A, do something about it, and then B, figure out how to avoid that situation again in the future. But I have, yeah, many other stories about accidentally deleting too much stuff and not being able to recover. Or, I should say, what I did to try to recover after crying about it for a little bit. Okay, so let's switch gears a little bit, and now we're going to talk about cracking passwords, but using a dictionary rather than a brute force approach. See, it's well known that when people are asked to pick a password, they're not very good at it. People don't usually pick, unless you're using a password manager, people don't usually pick a password that has just random jumbles of characters in it. They're more likely to pick a password based upon a common word or a word that they can remember. And if forced to, they'll just modify that word a little bit. Like they might think of the word puppy, right? But you can't use the word puppy, it's too short. So maybe you'd use puppy added with a few digits on the end, or you maybe put a $ in the middle of it, right? Some little transformation on that word in order to turn it into a password that's acceptable by the system you're logging into. So what I'm getting at is it's well known that humans tend to just use words as the basis for their passwords. And so that makes the job of somebody who wants to crack a password easier, because they don't have to try all 11 million permutations on a 5-letter password. All they have to do is find a list of common passwords and try those. And chances are one of those is going to work. So where do you get such a list? Well, there's a famous one out there called the RockU file. Because it was there was a website out there at the time in 2009 called RockU. That was the name of the website. And so now you can go and you can download this file. Here it is downloading. It's 133 megabytes compressed. No, it's not. That's uncompressed. So it's 133 megabytes. And when you view it, you can see that it contains lists of at least what were common passwords from that website in 2009. But unlike some of the password lists that you can get these days, This one is arranged not in alphabetical order, but in order by popularity. So the top passwords, the ones near the top of the list, were the passwords that were more common, and the ones towards the bottom of the list were the ones that were less common. So let's take a look at this. Now, I want you to guess first, what do you think, at least in 2009, what do you think was the most common password? And this is, now we're looking at, 13 years ago. What do you think was the most common password? So we'll take a look at that in just a second here. Once you get your guesses. Some of you probably know, actually. You've probably seen this file before. So the most common password, at least back in 2009, was 123456. Followed by 12345, followed by 123456789, and then finally by password. And you can see that the top 10 or so passwords, the 5 of them are just digits, and the others are just like common words. And here's Rock You, right? The name of that website. Down here is QWERTY, and then we've got Jessica, Baby Girl, Nicole. And periodically, researchers, security researchers, kind of redevelop this list and come up with the top 10 passwords for 2021 and the top 10 passwords for 2022. And if you look at those lists, you can see that the top 10 passwords for each year really hasn't changed very much. People are still picking passwords like these every day. So it's known that these are passwords that people actually use on websites. So if we can use this list, we could crack a whole bunch of passwords, because it's very likely that the passwords we're trying to crack come from passwords like the kinds you find on this list. So in our assignment, we're going to be working with a shorter version of this list. The actual list itself contains about 14 million words in it. But what I've done is I've taken that file and I've shortened it down to one that contains, let's say, 100, the top 100. And I've got also like the top 1,000 and the top 5,000 words out of that list. So what we're going to do is we're going to write a program that will use that dictionary list of words to try to crack a hash. So let me go and get the assignment. Now, those of you who are following along on YouTube, you can actually clone this assignment yourself. Just got to find it. Where are we? We're way down here at the bottom. Here we are. So you can clone this repository. Now, if you're one of my students, you're going to have an extra step to do this. But anyone can go and use this address here to go and clone this repository. Oh, you don't see what I'm doing here. Sorry. Here we go. This is the repository. So you can just use git clone and then this address right here. Oh, you'll leave off this part right here. So let me show you the actual thing that you'll use. It'll look like this. Git clone https bit bucket.org Boffery Brown. What's it called? Crack 2. Okay, but if you're one of my students, there is an extra step involved. So if you're one of my students, you are actually going to want to do something called forking this repository, which is to make a copy of this repository, but in your own Bitbucket set of repositories. So I think that is, now they've moved stuff around yet again, but somewhere there's a menu here that says fork this repository. Where is it? And maybe it doesn't show it to me because this is my own repository, so why would I want to fork it? They keep moving stuff around. It's kind of annoying. See, I don't want to clone it. I want to fork it. So usually, right? Oh, here it is. Yeah. How could I have not seen that? So under this ... menu, there is fork this repository, and what it will do is it'll make a copy of this repository, but in your Bitbucket set of repositories. And the reason for that is, although you could clone this repository, when you try to push your files back up, it'll try to push it to this one, and you don't have permission to push files to this one. So you're going to want to make a copy of this repository yourself so that when you push things up to your repository, it'll go right in. So you're going to go to this ... menu, say fork this repository, and then just click on fork, and then you're done. And then once you've done that, you then click on the clone button, and you can copy this address, come over to your environment, and then paste that in. And of course, it's going to have your username here, not mine. So let me go and erase that. And now we've got a copy of my repository, or your repository, on your IDE system, and you can start working on it. So what I would suggest you do, if you're using my environment here, is we've now got this directory here called crack2. I would suggest that you open up a new workspace, a new window, just in that directory. So if I go and click here, open workspace, and then find that crack2 directory and click on open. Oops, I need to go and log in again. I need to refresh this. Here we go. That should do it now. Open workspace, crack2, open. There we go. So this has opened up a new window or a new tab, and it's now looking at just the files for this project, for this assignment, and it's not showing you all the other stuff. That stuff is still over here in this tab, but now we've isolated it to just the files for this assignment. And you can see here that I have 4 versions of the RockU file. I've got one with 100, the top 100 in it. I've got one with the top 1,000 in it, the top 2,000, and the top 1,000,000. And I've also got a program here called crack.c. We'll take a look at that in just a moment. One called hashpass.c, and then a makefile. So let's ignore those for a moment, and let's get started on not writing the program that you need to write for this assignment, but one that's similar, one that's going to use the dictionary, but it's going to crack the one password that we pass in, the one hash that we pass in on the command line. So it's going to be kind of similar to the brute force one we wrote last time, but instead it's going to use this dictionary. Let's call this crack word. I'm just going to write this from scratch. The actual program that you have to work with, I've given you a template program and you just have to fill in the blanks, but we're going to write this one from scratch. I know I'm going to need standard IO, and I'm going to need standard library, and probably string.h since I have to do string comparisons. And finally, I'm going to need md5.h. So those are the 4 includes that I know I'm going to need right off the bat. Now I want to be given the hash to crack right on the command line. So I'm going to need to write my expanded form of the main function that allows me to accept command line parameters. I need to check on something here. Just a moment. Yeah. That looks okay. Okay, where were we? We're back. So the hash that I want to crack comes from the command line argument. It comes from the command line. So the first thing I should do, it really is just check to make sure that the user actually typed in something. So I'm going to check the value of argc, and if that is less than 2, if there's less than 2 things written on the command line, then I want to print out an error message. And usually the way these error messages look is it's something like usage, then the name of the program, and then finally any command line options that you want to pass in. We'll call this like hash to crack. And I'm going to pass in argv0. So what it will do here is it'll swap in the name of the program, which comes from the command line, and put that right into my usage message. Let's go ahead and compile this so you can see what it looks like. So if I just run it without any command line options, it tells me how to use it. Usage ./a.out. Notice that's the first thing that I typed in on the command line. And then hash to crack, which is just some text that I've written into the string itself. So if I was to compile this program and call it something else, and then run that, it puts in the actual name of the program. So argv0 is the name of the program that was used to invoke the executable. It's kind of a cool thing you can do there. Okay, so now that we've gotten past that, we know that we have a hash on the first command line argument. Let's go ahead and make a variable that points to that. Call it target. So whatever string is sitting in argv1 is just going to be assigned to the target variable. Let's see what to do next. So we have the hash we want to crack. We now need to open up a file and start reading through that file and use each one of the words that we found there in order to crack this hash. So now we're going to open dictionary file. So file pointer, let's call it D equals fopen. Which one are we going to use? Let's use the rocku100 file. And we're going to open that for reading. We should check to make sure that we were able to actually open this file. I could have mistyped the file name, or I might not have permissions to open it, or something catastrophic could have happened and the file doesn't exist anymore for some reason. So let's check to make sure that we were actually able to open it. And if not, we'll print out an error message and then exit. So we'll do it like this. We'll go character error 100 sprintf into the error string. Can't open %s for reading. So here's what I'll do is I will make a define. We'll say rocku100.txt. There we go. Now I can just put that inside of a constant that I can change very easily. And then we'll go p error with my error message. So if I can't open that file for reading, it will display an error message that says can't open, rocku100.txt colon, and then the reason why. And then finally we'll exit. So let me show you what that looks like. Let's go ahead and change this to something that doesn't exist, like rocku200. That doesn't exist. So if I type in a hash that I want to crack, and I can use, let's say, this one, then it says can't open the rocku200 file.txt for reading, no such file or directory. So that's a nice error message. It tells me what's going on. It can't read the file, and then why it can't read the file. So if I go ahead and change this to the file that does exist, then I don't get that error message. So that's good. Okay, so I got the file open. Now what I'm going to do is I'm going to read through that file one word at a time. I'm going to hash each one of those words and then see if it matches my target. So for that, I'm going to use a loop. Now I don't know how many words there are to begin with. I don't know whether there's 100 or 5,000 or a million. So the best thing to do would be to use a while loop that just loops until it hits the end of the file. I'll use fgets to read each word out of the file. So which means I'm going to need a string. Let's call this, I guess we'll just call it word. And we'll set aside 100 characters for it. All of the passwords in this file are going to be less than 100. In fact, they're going to be less than like 20. So 100 should be good enough. So as long as fgets is able to read in a word, it will return a non-null value back to us. So as soon as we hit a null, we know we've hit the end of the file, and we can then stop at that point. Okay, so we now have a candidate word sitting in the word string. We have our target hash sitting in the target string. We need to turn that word into a hash and then see if they match. But the first thing to do before we do that is to strip off that new line character. When we read a word out of the file, it's going to have a new line character on the end. We don't want to include that in the hash. So we're going to have to get rid of that. Remember how to do that? Use the string character function to search for that new line character. And then if it exists, set it to the null character. So search for the new line character out of our word. We're going to get back a pointer to it. And then if we got an actual pointer and not a null value, we're going to change it to the null character. I always put this condition in because there's a slim possibility, not really with my program here, but it's a good habit to get into. There's a slim possibility that the word that we get back from fgets does not include a new line character. That could happen in two cases. One is it could happen at the end of a file. Sometimes there's no new line character at the very end of the file. And the other is if the line that it read in was longer than the string that we had set aside, it also won't include the new line character. So it's a good idea to make sure that you've actually got a new line character there, because there's two ways that it could maybe miss it. Okay, so now we have a candidate word. The new line has been stripped off. We can hash it and then see if it matches. I'm going to call my MD5 function. This is the one that's defined in MD5.c. And then we are going to pass in the word that we want to hash along with its length. and then we get back a pointer to the hash. And now all we have to do is just see if they're equal to each other. So if string compare hash and target is equal to 0, oops, then we found it. Found, I'm going to print out two things. I'm going to print out the hash that we wanted to crack, which is target, and then I'm going to print out the word that we actually found. And then at that point, we're pretty much done. So we could close the dictionary and then exit the program. Otherwise, we're going to keep looping through all of our dictionary words, and if we get all the way through that loop and we never find the dictionary word that matches the hash, then it means we didn't find it. Or we'll just say not found. And then we can close our dictionary and then exit the program. Okay, so that should be our program that cracks a single hash. Let's go ahead and compile it. Now to compile it, we're going to say clang, crack, whoops, here it is, crackword.c. We also need to compile in the md5.c file. Oh, and then link it to the crypto library. So let's try to crack this hash. Now we know that the word is going to be March. And it says, oh, I didn't find it. I think the reason there is because I'm only using the rocku file that contains 100 hashes in it. And I'll bet you March is not in there. Let's just go and look at it really quickly. Let's do find March. Yeah, it's not in there. So what we need to do in order for this to work is we need to pick a word out of here that does exist, hash it, and then try to crack it. So let's pick bubbles. That looks like a fun one. Let's go over here and we're going to hash it. So here's the hash we want to crack. And then there, we found it. Found this hash, and there's the password, bubbles. Let's pick another one. Let's pick basketball. So we'll go over here, paste that in. Here's the hash we want to crack. Basketball, we got it. Okay, so we've just developed a program here that uses a dictionary to try to crack a password. Now, of course, the word that you want to, or the password you want to crack has to be in that file somewhere. If you pass in a hash that doesn't exist for any password in there, it's just going to say it's not found. But nevertheless, this does use a dictionary to try to crack some passwords. Okay. It's 11 o'clock. We're going to take a short break, and then when we come back, we will look at the current assignment, and we will then go over what you need to do to complete the assignment. I need to get something to drink here, so we're going to take like a 5-minute break, and then we'll come back.
Recording stopped.
All right. I haven't heard from you guys in a couple of minutes. Just watching what I type in. Is there a C equivalent to Python's if the name of the function is main, to write main? No, there isn't. You just have to write main. You just have to write your main function. I mean, the idea in Python is that you don't have a main function to write. You can just write your statements like not in their own functions. And then essentially what the Python interpreter or compiler does is it collects everything that is sitting by itself, not within its own function, and it just assembles that into a main function and essentially writes it for you. So it takes all the standalone stuff that's in your script and then just puts that into a function called main and then just calls that. Abdul says, how do I make the make command work on my machine? So what are you running? Windows? Mac? Linux? So we can help you if we know more about your machine. Yeah, we've got Windows. So I think the thing to do would be to install the Windows subsystem for Linux. So if you just Google for that. There's a button here that says install WSL. And then it takes you through the steps to do it. It's pretty easy. Any tips for Sigwin? Same idea. But it's been a while since I've tried Sigwin, but if I recall, there was an installer for Sigwin. So you run the Sigwin command, and then it brings up like a dialog box where you can pick what packages you want to install. And there it would just be a matter of finding the development packages, selecting them, and then clicking on install. Then it goes and downloads them and puts them in your system. Oh yeah, so run the setup program. Choose packages and download them. Does it look kind of like this? Here, you finally get to a screen that looks like this. And then you can find this development package and then go and find the packages you need. Or you can just select all the development stuff. Just do a select all there. Pull it all down. I see, you probably don't want to do that. Actually, you get a whole bunch of stuff you probably don't need. Like a Fortran compiler. You probably don't need that. But C compiler, C++, those would be good to have. GDB, make. What are DLL files? DLL stands for dynamically linked libraries. So they are, well, you know, they're kind of like the libraries we've been linking into, like the crypto library. Except on the Windows systems, those would probably be called DLLs, because if there's ever an update to the crypto library, you don't have to recompile your programs all over again. You just download or install those new DLLs, and then the next time you run a program that uses that library, it'll just get linked in automatically. So DLLs are basically library packages that can be swapped in and out of your system whenever there's an update, and you don't have to recompile all the programs that use those. Linux has its equivalent. They're called .so files, shared object files. And the idea is the same, is that when you have an update for one of these libraries, it just swaps in the files, and then the next time you run a program that uses one of them, it'll link to the new one instead of the one that was originally compiled with. Yeah, similar to SO files in Linux and to DYLIBs on the Mac. SO stands for shared object, and DLL or DYLib stands for dynamic libraries. Same idea. Let's see, let me look through my chat and see if there's anything else we missed. I must say, developing C programs these days is just a whole lot easier than it was back when I was doing it. Back when I was doing it, we didn't have integrated development environments because we just didn't have graphical user interfaces. I mean, we did with our personal computers, like we had the Mac, right? And Windows had Windows 3.1 at the time. But it was, and you could get C compilers for it, but all of our programming courses that we took in the university environment had to be done on a Unix or Linux system. So we had to use the command line C compiler. They told us if you want to develop on your own computer at home, if you have one, that's fine. You just have to make sure that it compiles and runs on the Unix servers that they have. So oftentimes I would do that. I had my own Mac, and so I was able to develop C or Pascal programs on the Mac, but then I had to ensure that it actually ran on the server. And of course, if I wanted to work with my friends, I had to do it on the server because I just couldn't just haul my computer over to the computer lab and plug it into the network because we didn't have that kind of stuff. So a lot of my development was just on the command line using the, well, now we would call that the Vim editor, but back then it was just called VI. And compilation was actually, compared to this day, slow. If you had a program that was, let's say, 1,000 lines long, which was not unusual for a larger data structures program or a compiler construction program, it might take 30 seconds to compile that program. I mean, it was not a trivial amount of time. I mean, still, it wasn't that long, but it kind of put a damper on just make one little tiny change and then recompile it. Make one little tiny change and recompile it. You might want to make it kind of worth it. And the other problem we ran into was, since the whole server was just slower than we have today and not as much memory, you simply couldn't support a class with 100 students on it simultaneously and expect everything to go smoothly. If you had a class of 100 students all trying to compile their projects, and each of those compiles takes 30 seconds, you know, the system's just going to slow down to a crawl because it's spending all of its time shuttling data in and out from the disk, compiling programs, putting the results back on disk. So the system administrators had developed this queuing system where you ran your compile command and then it got stuck into basically a queue or a line of compile commands that needed to run. And so you type in your compile command, and then you get this message that says, you know, you are number 35 in line. And then you'd watch this message tick down. You're, you know, a minute later, it says you are number 34. Literally, it might take minutes for your compile command to actually run. So you'd issue the compile command, and then you watch this queue decrease, this number decrease as you approach the beginning of the line. And, you know, hope you didn't just hit Control-C somewhere in there and get out of line, right? Sometimes you might find that you issued the compile command and then you found a bug in your program as you're just waiting, right? You're looking at the program, oh my goodness, there's a missing semicolon. I need to fix the problem and then go reissue the compile command. So you press Control C and boom, now you're out of line and you got to start all over again. And it literally could take half an hour to an hour before your compile command finally got to the front of the line and then ran. So, you know, imagine you're coding along, you're like, okay, I'm ready to compile now, and I know it's going to be half an hour before I get the compile to finish. So you really wanted to make those compiles worth it, right? You visually looked over the program, you looked for every possible error you could possibly find. There were some other commands you could run, like lint and a few others that would just kind of like take a cursory glance at your program just to make sure it was most likely going to compile before you actually committed to getting in line to compile the program. But boy, that was just a completely different environment than today. I did find some ways around it, I mean, being the resourceful hacker that I was back then. One thing I discovered was that if you got in line to compile your program, of course the compiler wouldn't actually run until you were at the front of the line. So the computer labs we were sitting in didn't have computers like we have today with windows that we could run. We only had one 80 character wide by 25 character high text display to work on. So you could really only work on one thing at a time. You could either be editing your files or you could be compiling them, but not both at the same time. So again, being the resourceful person I was, I discovered this program called Screen. And what Screen lets you do is set up almost like virtual windows, windows being like views into your shell, but it allows you to run multiple shells at the same time. And you just press a couple of keystrokes to switch amongst these different text views. So I could literally have a text editor running in one window, let's say pane number 1, and then I could have my shell running in pane number 2. And so what I would do is I would edit my program, get it ready to compile, or I would get it ready, almost ready to compile. I would know, like, I got 5 more minutes of stuff to do on this. I would switch over to the pane that had the compiler running on it. I'd issue the compile command and get in line. And then I'd go back to the other pane and keep working on my program, because I knew it wasn't actually going to run the compiler until I got to the front of the line. So that gave me anywhere from like 5 to 15 minutes to keep working on my program. And then I'd monitor the line, right? I'd see the number ticking down, 34, 33, 32, 31. And then just before I hit the front of the line, I'd go save on my editor and let that go into the compiler. And so that allowed me to compile like a whole lot faster than my classmates could. Right? Because as soon as one compile was done, I'd immediately issue the next compile command and then start working on my program to fix the bugs I had just discovered. So while my classmates were compiling, you know, every 30 minutes, I was compiling like every 5 minutes, right? Because I would always get in line. And if I discovered that I wasn't going to have my fixes done in time for me to get to the front of the line, I'd go ahead and get out of line and then reissue the compile command, get back to the back of the line, and then start all over again. So that was Compilation Adventures back in like 1990 or so. Are the arguments the same for GCC versus Clang? They are. They're almost completely compatible with each other in that case. Are compilers much faster today? Oh my goodness, yes. You can see here how we can compile a program in a fraction of a second today, and that would have taken, I mean, even the programs that we've written here, you know, like the ones I've got on the screen here, I mean, this probably would have taken 30 seconds to compile. So yeah, they're much faster today, and it's changed the way you do compilation. Nowadays, you just make one little change and you recompile. You make one little change and compile. In fact, some IDEs are actually compiling as you go. Like, what is it, IntelliJ? Right? As you're typing your program in, it's just running the compiler almost continuously in the background, so it can catch errors as you type them in. You know, as you omit a semicolon, you go to the next line and boom, an error message pops up and it goes, you missed the semicolon, right? Because it just compiled the program in the background. So it's always compiling your program continuously and finding errors as you go. That like didn't exist at all back then. Yeah, the 90s were the best, right? The computers were simpler. They were kind of easier to maintain. It was hard. It was easier to kind of like understand what was going on. And now they're just so complicated. But you can't live without them, can you? Oh, this was back in the this was back when spam didn't exist, right? We had email, but spam did not exist. It was not a thing yet. The very first computer worm, I mean, that just made huge headlines when that came out around 1989, 1990. The very first like self-replicating program that could spread from computer to computer. That was huge news back then. Did I write my code in the VI editor? Yep. Pretty much all of my programming was spent in that. Some of my friends knew Emacs, and they would use that one. They tried to convert me too. I just never got into Emacs. I mean, like I learned the keystrokes for VI, and I figured to learn Emacs was just unlearning a whole bunch of stuff and learning new stuff, and it just seemed like not a good use of my valuable time at the moment. So a lot of people said, learn Emacs. Once you get into it, you'll be so happy that you learned it. And it's like I learned VI and then I got along just fine. To this day, I still use it. I know how to get out of Emacs, so I accidentally find myself in it. Control X, Control C is how you get out of Emacs. It's kind of like in VI. If you don't know VI, you need to know how to get out of it. Like Shift, was it Shift colon Q exclamation mark? Will get you out if you find yourself in it. Oh, so the 90s was also back when there was no internet as we know it now. So, I had a modem for my computer, and I could dial into the Unix servers. But again, it was just a text-based dial-in. It wasn't like web browsers. That didn't happen until like 1993, 1994 that we started getting web browsers. So the first 4 years of my college was no internet. If you wanted to look something up, you had the online manual pages, which you got to by typing man and the name of the command, or the computer labs just had bookshelves of manuals that you could go over and you could just read. Yeah, Shift-CZ is also a way to get out of VI, but if you found yourself in there and you accidentally started making changes to a file and you want to get out and undo all those changes, then colon Q exclamation mark means I want to quit and not write my changes out to disk. There was another text editor at the time called Teco, T-E-C-O. And a couple of I'm going to say one of my friends was really into that one. And that one, again, that was kind of like an editor for the ultra nerdy people. I mean, VI had like this steep learning curve. You had to learn about insert mode versus command mode and how to move the cursor around. And we didn't have cursor keys either, or we did, but they didn't do what we wanted because VI didn't understand how to use the cursor keys. So you had to use H, J, K, and L to maneuver around the screen. You got pretty good at using that. A lot of kids these days ask, why not use WASD? Well, that didn't come around until maybe the 2000s, using WASD to navigate. Before then, it was H, J, K, and L. Those are 4 keys that are right on the home row. And so H goes left, L goes right, J goes down, and K goes up. And so you got pretty good at navigating using those. But Teco, what can I say about Teco? Teco had a really esoteric and bizarre command structure, and there was kind of like this game you would play if you were a Teco user. Is you would launch Teco and you'd like type random gibberish on the keyboard and then attempt to predict what it would do to your program, and then you press enter and see if it actually does that. right? Because basically any random gibberish you could type in on the Tico command line was a valid set of Tico commands. Do things like, move to line number 5 and replace character number 6 with an X, and then move down to line number 10 and delete that line. So that was a game that my friends would play. Can anyone suggest me the best source to learn Linux, terminal, and bash script? And you'll have to lean on the other people in the chat for that. I mean, for me, it would be find some tutorial online that will get you the basics, like how to navigate the directory structure, how to issue commands, and then just go from there. And then every time you run into a problem where like you don't know what to do, then you look up how to solve that problem, and then you go from there. So you just try to kind of like get along with what you have until you go, there's got to be a better way. And then there probably is, rather than trying to learn the whole thing. There's no way to learn the whole thing. So just learn what you need at the moment and then add on to that knowledge later. That's the way I learned. When I was first started using command line back in the 80s, they handed us this packet of papers about 10 pages long. And they said, here's how to type in your programs, compile them and run them. Here's the 15 commands you should know. Learn it over the weekend. See you next week. That was our introduction to the command line. Okay, let's take a look at the assignment for this week. So I'm going to unpause my Zoom recording, and then we will pick up where we left off.
Recording in progress.
Okay, so here is the assignment we're doing this week. I already showed you how to obtain the starter files. You need to open a web browser and go to My Repository on Bitbucket. You're going to fork the repository to make a copy for yourself, and then you are going to clone the repository into your IDE. Next, you're going to run this command called make hashes. Let's go over to that terminal over here. I'm going to type in make hashes. And what that's going to do is it's going to invoke the Makefile. It's going to compile a program called hashpass. So there's actually two executables in this assignment. There's the one that you're going to develop, and then there's one that I've given you called hashpass. And its job is to do what you did on the previous assignment from last week. What it does is it takes a file full of passwords, plain text passwords, and it hashes each one of them and turns them into the corresponding hash. So the first three commands are to compile the program called hashpass. Then it takes the rocku100 file, shuffles it up, so it randomizes the order, and then pulls off the first 20 elements of it, the first 20 lines, and puts them into a file called passwords.txt. Let's take a look at that. So here's the rocku100 file. And then here's passwords.txt. So it is pulled off after jumbling up the order of the 100 passwords in the rocku100 file. It's pulled off 20 of them. And then it runs your hashpass program, uses the passwords.txt program as input, and then outputs to hashes.txt. And let's take a look at that. So here is 20 hashes that your program now needs to crack. Now, we know what the answers are. They're sitting in the passwords.txt file, but your program's not going to use that at all. It's just going to try to crack these passwords based upon the words that are in the rocku100 file. So we've got 20 random passwords picked out of the rocku file. Those have all been hashed, and now your program needs to try to crack those. Let's take a look at the program that you need to write. So this is crack.c. I love this part of the semester because we get to talk about like making crack and making hash, and then your friends and relatives look at you like you're totally strange. Anyway, so let's look down at main. So in main, it checks to see if the number of arguments is less than 3. If it is less than 3, then it gives you a usage message, very similar to the one we wrote in the program about an hour ago. you pass in two command line arguments. You pass in the name of the file that contains the hashes, and you pass in the name of the file that contains the dictionary. And then there's some comments in here for you to fill in the rest. Open the hash file for reading, and of course also check to make sure you were able to successfully open it. And then read that file in one line at a time. For each hash in that file, crack it by passing it to crack hash, and that's going to be a function that's also in this program. And then display the hash along with the crack password. So display the hash itself, followed by the word that it corresponds to. Close the hash file, and then free up any malloc memory. So try to get it so that if we run valgrind on your program, it says that there's 0 bytes left over at the end of the program. Let's look at crack hash. So crack hash is a function that takes in a target hash as an argument and the name of the dictionary file. In this case, it's going to be Rocky 100. You're going to open the dictionary file, loop through the dictionary file one line at a time, hash each password that you found there, compare to the target hash, and if they match, return the corresponding password. And then finally close the dictionary file, and then free up any memory if you have to. So you're going to replace this return null with something real there. This is just there so the program will compile, but you're going to replace this with something to actually return. So this is a pretty straightforward program to write. As an example, we wrote a program that will crack a single hash. Hi.
Hi.
How you doing?
Good. Keep teaching, keep teaching.
How are you?
Good.
Yeah, the puppy's been keeping me company here.
I was looking for the dog.
He's got something stuck to his ear.
Sorry. I was looking for the dog, actually.
What do you got here? Oh. She came in here to look for my dog. Or look for our dog. Got a piece of tape stuck to his ears. Okay, so where was I? Okay, so you need to write a function called crack hash. This is going to be a fairly straightforward program. We already wrote a program that can take one single hash and open the dictionary, read through the dictionary one line at a time, hash each one of those words that it found, compare it to the target, and then display whether it cracked it or not. But this time we're taking that program that we wrote and we're making it its own function, and the purpose of that function is to open the dictionary file, loop through that file, find the corresponding password, and then return it. Now, those of you looking at this probably can see, oh, there's probably a whole bunch of places here where we could optimize this. We're going to be working on that over the next week or so. Right? Some obvious optimizations are, why do we have to open the dictionary every single time? Could we open the dictionary just once and maybe save a little time there? I wanted to make this program pretty straightforward to write. There's a couple of twists in it, a couple of things you'll have to work through, but for the most part, it's pretty straightforward to write. And then we're going to work on optimizing the heck out of this thing over the next week or so, week or week and a half, so that it can not only crack many more passwords, but it's also a lot faster. So this is what we got for now. We'll work on optimizations later. Okay, so that's the one program we have to write this week. That's it. We're taking all the concepts that we've learned over the past week or so and putting them together. We've got, what do we got here? We got opening files and reading files. We've got string comparisons. We have calling library functions and compiling the program, and also makefiles. And so let's go take a look at now that I'm reminded, let's go take a look at the makefile. So in the makefile, there's some variables that you can change. You can change the number of random hashes that are chosen. You can change which Rocky file is used. By default, it's the 100, but you can change it to use the 1000, 2000, or 1 million file. All you have to do is just remove the comment character from the line that you want to enable, and then put in a comment character in front of the one that you want to disable, so that only one of those lines is defined at any one time. There is a target up at the front called all, and the only thing this does is invoke the hash pass target and the crack target. That's all it does. There's no actual like command for it to run. So when you type in make, it compiles those two programs. Okay, but here it shows an error message because there's actually some parts of the Makefile that you need to modify. Here are the commands to compile and the hash pass program. And here are the actions for the crack program. These are incomplete. You need to fix these. So in this section here, line 29, you're going to remove these lines and then replace it with a command that will be used to build the crack executable out of crack.o and md5.o. And then down here, you're going to put in the action to build crack.o out of crack.c. So there's two places for you to put in some compile commands to make this Makefile work. And then finally, we have these actions to like build the hashes file, clean everything up, so to remove the .o files and the executables. You can also say make test, and it will run the crack program using the hashes file that it built and the rocku file that you defined. And then there's also a make check that you can type in that runs the program but uses Valgrind instead. And this is what you can use to detect those memory leaks. So you want to go for 0 memory leaks at the end of the program. So if you've got everything running, you can just type in make check or make test, and it will compile and run your program, and then you can look at the results. Okay, so in the Makefile, there's just two things for you to do. You're going to replace lines 29 and 30 and 36 and 37 with compile commands in order to build these targets out of these dependencies. And that's it. That's the assignment for this week. So coming up in the next couple of weeks, we have sessions on the coming Tuesday and Thursday, where we're going to talk about optimizing this password cracking program. And then here in the United States, or at least at my institution, we have 1 week off. So the week of the 11th through the 15th of April, there's going to be no live sessions that week. We have our Easter break. So the 1 week off from classes before Easter on, what is that, April 17th, I think it is. And then we'll be back the week after that. So starting the 18th, 19th, 20th, we'll be back doing the live sessions again. So we got 1 week off where there's going to be no sessions. And then from there, we'll continue talking about this password cracking, and we're going to start to move into networking. So writing programs to send data back and forth over the internet. And so that'll be pretty cool to be able to do that as well. And then that should take us roughly to the end of the semester. I think we'll have about a week or a week and a half at the end of the semester where we kind of have nothing scheduled. That's, of course, to give my students time to finish up their assignments, but it would be time for us on these live streams to just do other stuff. I could show like more advanced C programming. I could show, one of the things I actually like doing at some point is showing how to program some of these old computers, like these old 8-bit computers. What was programming like back in the early 1980s and late 1980s on these old computers? I can actually bring those, I can hook them up to my video equipment, and we can show what's on the screens over there. So that would be like a fun day when we do that. I'm actually, in my voluminous free time, which is almost none, I'm working on a program in BASIC, Apple BASIC, that would run on like one of those computers back there. You can just barely see it at the bottom of the screen, but there's an Apple computer down there, and it plays Wordle, right? You know, the current, guess the 5-letter word in 6 guesses game that's going around. So I'm working on a program to do that, and the actual, I'll also tell you, the actual Wordle part of it is not that difficult. The actual part that like takes your guess and compares it against the word and sees, which letters match up and which ones are in the wrong positions. What's been the most difficult was actually searching through this large dictionary of 2,000 or so candidate words and seeing whether the one you're looking for is in there or not. Turns out that searching through a list of 2,000 5-character strings takes about between 15 and 30 seconds. So it's like type in your guess and then wait a long time for it to tell you whether or not your guess was right or not. And so what I've been kind of working on is how can I speed that up? You do it on a modern computer, searching through that list takes like 1/100th of a second. Do it on these old computers, it takes 10 to 15 to 30 seconds to do. So how can we speed that up? And of course you're thinking, well, do some kind of binary search. Well, to do binary search, I now have to sort that list. So I quickly wrote up a bubble sort program last night, and I calculated it was probably going to take like a day or two to sort that list into alphabetical order. So I now need a faster way to sort. So I'm trying to code up quick sort. And that's been taking some time because these old computers, at least the old BASIC on them, you don't have recursion. Well, you do have recursion, but you can't go very deep. You don't have local variables. So anytime you do call a subroutine, you have to figure out how to recycle your variables. And also you have very limited memory. The actual list of words itself takes up almost half of the available memory. And so you don't have very much left over to be able to write your program. So it's all this juggling to figure out in severe resource constraints how to get your program to work, to run, and to fit in there. So I've been having fun with that. And so I think I might show you the fruits of my labor here in a few weeks. Can we look at how to implement Minimax and Negamax if there's time? Okay, I'll look into that. You have to remind me again. I'll probably forget, but I'll look into that. Okay, I think we've kind of reached the end of today. Why don't I go ahead and say goodbye to the Zoom folks. And then I'll say goodbye to the YouTube folks. All right, so that's the end of today. I don't see any questions on the chat, so we will return on Tuesday, and we'll continue talking about this program. I would like you to start on this assignment as soon as you possibly can so that we can go over any questions that you have about it as soon as possible. If you wait too long on this, then you'll find that you end up kind of maybe get stuck at somewhere, and then get stuck on it somewhere, and then it's kind of difficult to get your questions answered. So if you can kind of catch up and get rolling on this, the programs are going to get more and more challenging as we go through the next few weeks. So it is a good idea to get caught up if you possibly can. Okay, so Zoom folks, I will see you later. See you on Tuesday. Have a good weekend, and be safe, and have a great rest of the day. Bye-bye. And YouTube folks. India, your companies are reopening in April. COVID is almost done. Yeah, we started reopening. I mean, we're pretty much back to normal as far as masking requirements and companies reopening. I mean, there's still a lot of businesses that are still cautious, so they recommend people come in with masks, and they still trying to get you to stand 6 feet apart, 2 meters apart from each other. But you can tell by the traffic outside that things have pretty much returned to normal. I guess the concern now is that new variant, the BA2 variant that's spreading around. We still have a very low rate of infection, but they said on the news that now that new variant of the people who are getting sick makes up over half of the people who are getting sick. So We're all kind of keeping an eye on seeing whether the number of infections starts ticking up again in the next, especially the next month, as students go to their spring break and they gather in huge crowds, and then they come back to their university campuses and they spread this stuff around. And we're going to see what happens. Okay. I don't see any other messages I need to catch up on. So why don't we end it here as well? Yeah, if you've been vaccinated and you've been boosted, you probably have nothing to worry about. It's just getting sick again, right? It's just kind of, just hate getting sick because I've spent the last 2 weeks not getting sick very much. And so it's been pretty nice, right? Only been sick a handful of times. All right. Lord Melbury, thank you for joining us. You have a good weekend. And Akash, you too. And I'll see you next week. Oh, you want me to complete the full C course? Just keep watching. We'll get all the way up through computer networking by the end of, see, we'll get to about mid-May or so. So we got about a month and a half left. And then I actually have a whole bunch of other live streams. Just go to my channel and you'll see a whole bunch of, starting in January. Well, we're on week number 10 now, so there's been about 18 live streams we've done up till now. All starting all the way from the basics, going up to what we see today. Okay, take care. Be safe. See you next week. Bye-bye.